All right, so we just completed the RC circuit example. This is a really similar example, but this is an RL circuit. Of course, I basically just replaced the capacitor with an inductor here on the output, and I'm also asking that we find V out of T, which in this case is the voltage across my inductor. And I'm saying let the initial current, right, through the inductor equal 0, which basically means there's no energy stored in this circuit. There's no initial conditions, okay? So similarly, we can start with the KVL loop around this circuit right here. So I would just start with Vn of t, which is 5u of t minus I of t times r minus VL of t equals 0. Of course, I'm looking for VL of t or VO of t in this circuit, so I want to represent my I of t in terms of VL of t. Probably easier to do that in the S domain. So again, let's do the transform here. In each of these cases, we know that this is going to become 5 over S. This is just going to be I of S times R for now, and then this is going to become VL of S equals 0. And so let's just recall that for an inductor, the voltage across the inductor as a function of t is equal to L di L of t dt, right? And so by time differentiation, we can go and determine how to find this, the S domain version or the transform of this function here. I remember it, but in case you don't, I'm going to go back and grab it from the table. So we look at the Laplace transform properties, and we want time differentiation, right? Because we're looking at L di dt, so we want this derivative here. Hopefully I get a good screenshot. Yep. All right, and then let's go back. So we're right here. And so the time differentiation property basically says that we need to take our function. So in this case, the constant's going to come along for the ride, but it's going to be S times f of s, which in this case is IL of s, minus f of 0 minus, so IL of 0 minus. In this case, IL of 0 minus is the initial condition for the current flowing through the inductor. We know that that's 0, that's given, so we can say that this is 0. So I can just say VL of S is going to be equal to S times L times I of S. And so I can write I of S is equal to VL of S divided by S times L. And so now I can substitute that expression over here. So I can say 5 over S minus, and now I'm plugging in, right? I'm plugging in VL of S over SL instead of I of S here, times R, right? That multiplied by R, minus VL of S is going to give me 0. And then I can get all these VL of S terms onto one side. 5 over S equals VL of S plus VL of S times, I'm going to write it as 1 over S L over R. And so I can say that that's VL of S times 1 plus 1 over S L over R. And now I can get VL of S by itself, and I can say that that's equal to 5 divided by S times 1 plus 1 over SL over R. I multiply the S through here, and I get 5 over S plus 1 over L over R. Or I could say that that's just S plus RL. But I'll just leave it as 1 over L over R for now. And here we are. We don't need to do partial fraction expansion here, actually, because we're already in a form that's really easy to transform using the Laplace transform table. Okay, so I'm going to leave this problem here, and we'll just wrap it up in the next video. I probably could just finish it right now, but I have an extra slide, so I figured I might as well just split it into 2 videos.